does our nucleophile do? Attacks the carbonyl carbon. We then break the pi bond to form our tetrahedral intermediate. It says tetrahedral, and that's as close as I'm going to get for intermediate. What happens then? We reform the pi bond, and we kick out the leaving group. And we end up with our final product. Okay? So depending on the nucleophile and on our starting carbonyl compound, we may expect to see a reaction, we may expect not to, because the energetics of your individual species may end up varying, right? Come on. So we've got some relative electrophilicities of those. Everything's been shown in relative order. You'll notice that this does have an extra interesting piece added to it. That extra interesting piece in this figure would be the aldehyde and ketone shown in the middle. Why are those interesting to show in this chart? They don't do the addition-elimination reactions. Okay. Why are we including them in this list? Because what they're trying to do is show their relative reactivity in comparison to the other functional groups. The reactivity of your ketone and aldehyde is higher than that of the carboxylic acid and the ester. Okay. Why? What do the carboxylic acid and the ester have that is different from the aldehyde and the ketone? They have resonance, which can stabilize the electrophile. That resonance makes them lower in energy and hence less reactive. Okay. If we go through and look at our acid derivatives all stacked on top of each other, you'll notice that in all cases our tetrahedral intermediate is roughly the same energy. Because in all of those cases, our tetrahedral intermediate is high energy because of a negative oxygen, because we broke that pi bond. So the highest energy species in our intermediate is the oxygen. In all cases, it's a negative oxygen. So our intermediate is the same energy. But what changes when we change our electrophile is the energy of our starting electrophile. As we make the electrophile more electrophilic, it goes to a higher energy, which then means the jump from our reactant to our intermediate becomes smaller, and hence an easier step to jump. Okay? So it's looking at that balance between both the nucleophilic strength and the electrophilic strength of our starting carbonyl. Kind of makes sense? Any questions?
Just out of curiosity, did that bottom reaction ever happen?
Would we expect the bottom reaction to happen?
I know it can because of like the O2 minus, but I mean it's on there.
So it is on the list because what they are trying to show is how big of a jump that is. Could we potentially cause that reaction to occur? Sure. Okay. But to cause it to occur, what would we need? A stupidly strong nucleophile to overcome that energy. To generate a nucleophile that strong, you're probably likely doing other chemistry instead. Okay? So within those conditions, are we ever likely to see that? No. Okay? Because we have a really bad leaving group, it's super stabilized, there's nothing to really drive that reaction to happen. Okay. Other questions? Okay. Let's redo the quiz. What about the reactant? You're saying, oh wait, blah, 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 blah. You're saying HO minus isn't as stable as with oxide? I would make the argument that those are relatively equivalent.
It's not more stable.
It's not more stable, but it's not more unstable. So we could potentially get product based on that reaction.
If they could
to say that a little louder?
It's an acid-base reaction.
It's an acid-base reaction. Just because you have a carbonyl and a nucleophile doesn't mean that you're doing nucleophilic addition elimination. It's an acid-base reaction. Methoxide is a strong base. It deprotonates the carboxylic acid, and you end up with the protonated structure. Okay. Watch out for those. What's the wow? All right. Question 2. Saw a lot of people with this answer. What did you do to get that answer?
Reduce the pi bond.
No.
Well, if it was nucleophilic addition, and then you would have to.
Nucleophilic addition at the beta position of carbonyl. And I would agree with you if that had been your starting material. That is not your starting material. What is your starting material? This structure. That oxygen makes the other carbon, or makes our carbonyl carbons, better electrophiles. As soon as they are now better electrophiles, that attack takes precedence over your beta position. Okay. Initially, when we ran those reactions, we could reference that as an electrophile. Okay. The carbonyl carbon was by far the faster result. Okay. By having our carbonyl carbon be reversible, we could get the beta addition. This isn't a reversible addition, okay, because our result is a very stable carboxylate product when our nucleophile attacks the carbonyl. Okay. So we are not getting that alpha-beta unsaturated ketone Michael addition stuff that we did in the previous sections. This is your straight nucleophilic addition and elimination. The question becomes, which of those should we nucleophilically attack with our nitrogen? The left or the right? Why should you attack the right one? The left one has resonance stabilization, which does what to the quality of that electrophile? Makes it less electrophilic. We should have our nucleophilic attack on the other position. And Ryan, you just asked about this, and I'm nervous that I didn't look at your question quite right. Is that what we just talked about?
Yeah, sorry.
Okay, good. Kind of what I would expect you to get eventually. You definitely have some protonation, deprotonation stuff to worry about. So don't panic too much, at least not yet, about that. Okay. Question 3. What would your nucleophile be? Bromide. Your leaving group would be? Your carboxylate, which is more stable? Bromide or the carboxylate? The bromide is more stable, which means no reaction. The other thing that you could do, run the reaction. Let's just say, hey, why not? Let's do it. You'd end up with the bromide, right? Which of these two structures is more electrophilic? The anhydride or the halide? The halide. If it's more electrophilic, what's going to happen? The reverse reaction. We're going to go away from our reactive species. That's why that ranking of those can help out. I didn't like that pen anyway. How about that upper right-hand one?
First degree or first primary.
Notice I'm drawing that big old nasty structure there because that is a possible answer. You should technically be drawing that because that is a big organic structure. But the more important aspect of this is your primary amine. KOH acts first as a base, which then makes our nitrogen a nucleophile, which reacts with our electrophile. We then do KOH again, and KOH in that last case acts as, oh, please reconnect, a nucleophile. Okay. Last one. Lithium aluminum hydride does what? It's a reduction reaction. In the reduction reaction of an amide, you end up with an amine. In the reduction reaction of a ketone, you end up with an alcohol. And we now have our answer. Okay? Questions? None? Can you draw some answers down? I'm going to pause the video. Oh, first one. I've had a couple people ask me in office hours what the heck is going on with this stupid parentheses thing. Okay. Why that's showing up now, I have no idea. Okay. But for some reason, the textbook has decided to start including that in almost all of their reactions. All we're saying is that that carbon needs to be repeated 3 times. So there's 1, whoops, there's 2, there's 3, and now I can go out to the other part. That's all it's saying by that. Okay. Don't get lost in it. Just repeat it 3 times. That's it. Okay. So now what is your nucleophile? As a hint. The oxygen is your nucleophile, which can come in and attack. We can break the pi bond, reform the pi bond, kick out the leaving group, and deprotonate. We would end up with, oh crap, a lot of carbons. 1, 2, 3, 4. End up with that as our final product. Did you get that? Good. What happens in the next one? Well, pretty much the same thing. We now have the acid. Next one. Rhymes with rame ring. Okay, as long as you get it.
Wait, how is it the same?
Why does the triple bond not act as a nucleophile? Is that what you're asking?
Yeah.
What about the triple bond would act as a nucleophile? When have we seen it act as a nucleophile before? What did the triple bond act as? Nothing. Triple bond didn't do anything. What did happen? A base deprotonated a hydrogen, which now converted that carbon into a nucleophile. Do we have a hydrogen in the structure that was originally given? So we erase all of that. That hydrogen is still present. It is an implied hydrogen. If I wanted that position to act as a nucleophile, what would I have to do? Deprotonate. What's the problem with deprotonating that acetyl group? You end up deprotonating the alcohol first. So you'd have a carbon nucleophile and an oxygen nucleophile. It's going to be a mess. Upper right, our nitrogen comes in, does the same general idea. This is one of my least favorite reasons why I don't like nitrogen. Our nitrogen comes in, we do our little substitution dance like we have in all other cases, and we would end up with our amide, 9 carbons, seriously?
Just leave it like that.
Okay. And we would have our final answer. You'll notice that it didn't leave it quite as simple as this. So say that, or in the question it says that you have to have 2 equivalents. And I'm adding a further question on it. Why do you need 2 equivalents? When the nitrogen first attacks, you would have this structure. Your tetrahedral intermediate with our negative oxygen, that's a negative, and our chloride. That nitrogen is now very acidic. What do we need to prevent it from acting as the leaving group? Something basic to come along and deprotonate it. What is something basic in solution? More nitrogen. What happens if you protonate that nitrogen? It is now positively charged. Can it act as a nucleophile? Nope. You need 2 equivalents because in the course of running the reaction, you kill one of your equivalents. Okay? Because it ends up acting as a base and a nucleophile in the same reaction. So you have to watch out for that. Whenever you're dealing with nitrogen, this is one of those tricky, stupid things. It shows up in the homework as well. If you're under acidic conditions in the presence of a nitrogen, it needs to be protonated. If you're under basic conditions in the presence of a nitrogen, you can keep it neutral. But as soon as it is acidic, you should be specifying that as a protonated nitrogen. Okay. Again, super important when you hit biochem. Now I got to erase all that, get my last question back up. What happens on this last one? What type of reaction is this last one? You drew out the product, you should have ended up with this, right? What functional group did we start with? What functional group did we end with? So we did a trans esterification. You'll notice that there's a little bit of an arrow pointing to the CH3O. What was the nucleophile in the case of this reaction? As a hint, it's in red. Okay, it's actually methanol was the nucleophile. What is going on with that CH or that methoxide at the bottom? That's being showed as a base catalyst to speed the reaction along. Okay? Why do we need a base catalyst? What is your transition state? If you look at the transition state, you'd have your negative oxygen, oxygen with, what is it, that isopropyl. That intermediate is highly unstable and very likely would result in the kick out of the nucleophile that you put on. So that's not very helpful. So what could we do? We could add a base catalyst. The base catalyst will do what? Remove that hydrogen so that, so that now when our negative oxygen goes to reform that pi bond, we can now kick out the other oxygen as our leaving group. Does it have to be a base catalyst? No, it could be an acid catalyst as well. If we went under acid catalyzed conditions, what would our first step be? Protonate the oxygen, good call. Which oxygen? Our carbonyl. This activates our electrophile so that we can then do our nucleophilic attack. Nucleophilic attack, We've got our bond, O, CH3H. Now what would happen? We would likely deprotonate our positively charged species. Now what? Kick out the good leaving group. There aren't any good leaving groups. Protonate the other oxygen. So now you've got a good leaving group. Okay? So, acid conditions, you should be thinking, oh God, I don't ever want to see those again. Because you've got lots of protonations and deprotonations you have to worry about. Under the base conditions, they go relatively straightforward because it's a nice nucleophile and just kind of does it. Okay. Is the question there because I need to draw out the whole mechanism?
Oh no, I'm just wondering why that one would get needed, not the other O. Like
Which oxygen do we protonate? Good question.
No, I mean I know why that.
No, why? Okay, you just said you know why that oxygen should get protonated. So tell me, why should that oxygen get protonated? Why should I protonate the red oxygen, not the blue oxygen? There's more sterics, which would suggest it's even more difficult for it to act as a base and pick up a hydrogen. I shouldn't be protonating that oxygen. Your answer begins with an E and rhymes with Librium. Equilibrium. It would go back and forth. You're in the presence of a vast concentration of methanol. That's going to push to keep getting here until we kick out that group. There's now such a small amount of this present that the reverse of that step not likely to happen. Okay. So it's going to come down to an equilibrium to drive that reaction forwards. Okay. Other questions? Okay, good. Then we can move into the really crappy ones. We've got the Hell-Volhard-Zelinsky reaction. Okay. Take a look at, it's a very fun name, isn't it? You can say it all together. 1, 3. 1, 2, 3. Wow, that was awesome. I should do that more often. Okay, yeah, Hell-Volhard-Zelinsky reaction. Okay. Take a look at what happened. When you look at that reaction, what occurred? I will accept that, yeah. It is an oxidation reaction. Keep going.
You added a, well, is it alkyl oxidation? I don't know if there's the
I did a substitution. Hydrogen for bromine. Have we seen a hydrogen for bromine substitution before? Yeah. What were those reactions called? We could look at radicals. This is not a radical one. We've seen one where it's not a radical. There's a big hint. It has a lot to do being near this structure. And that position is labeled, we have an alpha halogenation reaction through an enol tautomerization. So that's an awful lot of reagents to include for just a standard alpha halogenation reaction. We should have just been able to add H plus and Br2. Been happy with it. Why do we have PCl3 and H2O being added in this reaction? And not only just being added, but in 2 steps. Because we've seen this before where it was just straightforward. In fact, we can even pick the simple example that we've seen before. Br2, H plus. The result, we've done our alpha halogenation. 1 step, Br2H plus. Why not Br2H plus up here? Are we protecting the alcohol? That's an interesting concept. What does PCl3 do? Replace what? Places the OH with a chlorine. Why do I need to do that? Why does this alpha halogenation work? We are forming a keto-enol tautomerization. We're going through the enol tautomerization. We have to be able to remove a hydrogen ultimately from the alpha position. Why with the carboxylic acid is that alpha position not acidic? The other hydrogen is more acidic, which could potentially be an argument behind that, but I would say there's a stronger one that might have to do with the atom next to that hydrogen. What does that oxygen have on it? Lone pairs. What do those lone pairs do? Resonance that stabilizes that carbonyl carbon. Do I need to do any enol tautomerization to stabilize that carbon? Nope, because the oxygen does resonance to stabilize it, which prevents the alpha position from being acidic enough to be removed to initiate the whole nucleophile process. PCl3 goes through and says, okay, fine, I didn't like the alcohol anyway, or the OH, and I'm going to convert that now to a chlorine. So good job on that, Maddie, you nailed that. Why is it now okay to do that alpha halogenation? It's even more acidic because very little, if any, resonance, nothing good, because we end up forming a double bond to a halogen, and we have an electronegative element doing an inductive effect on it. That hydrogen becomes more acidic. It is now activated to the point where I can do the enol tautomerization, which means I can do the bromination, okay, my alpha halogenation reaction, and I would end up generating after step 1, again, yeah, in all honesty, when you guys said that parentheses thing had happened a whole lot this chapter, I was like, no, you're wrong. Who knew? We can do the alpha halogenation, but that's not what our product is. How did we get to our product? Step 2, nucleophilic addition and elimination. Why does the water attack the carbonyl carbon and not the position where the bromine is? The more electrophilic at our carbonyl carbon. So we end up doing the nucleophilic addition and elimination to get us to our now brominated position. One of the neat things on this, we get a massive yield, okay? Huge yield on this. Okay? So we're taking advantage of that same enol chemistry that we've seen before, except in this context we have to switch out of the carboxylic acid because that oxygen stabilizes that carbonyl too much and it prevents the enol tautomerization. As soon as we put a halide on there, we have the enol or the enolizable hydrogen again. We can then go through our reaction. Okay? Kind of a neat little system they went through. Why they had to get their name attached to it, I don't know. But they did. I would likely guess that this reaction was all caused because they were trying to do some kind of weird bromine or chlorine substitution somewhere else in the structure, and bromine happened to be present, and they accidentally discovered this. That would be my guess. I doubt anybody went, oh yeah, if I just do this, it's going to give me this product. Okay. So there's our answer. Our carboxylic acids are not enolizable because you have that resonance stabilization of your carbonyl in the carboxylic acid. The acid halide does have that enolizability because we don't get stabilization of the carbonyl carbon. At least not a significant amount. So because we now have that enolate chemistry, we can continue that forwards. Questions on that? Cool. We've talked about these before. Our sulfonyl chlorides, in fact our sulfonyl chlorides, they make reference to mesylates, tosylates, and triflates. All those are referencing is what piece is attached to your sulfur compound. These are typically used because, number one, they are phenomenal leaving groups, and in some cases, depending on the structure, they can be sterically hindered enough to prevent other reactions as well. Okay. fairly standard chemistry. When we looked at it, we focused more on which end of the reaction, which part of this reaction. We're like, oh, this is where everything's happening. Oh, actually, does it show? Oh, shoot, it didn't take it all the way through. We kept our focus on our carbon-containing structure with the alcohol. When we got to the end, what did we end up converting the oxygen to? A good leaving group, which means we can run what type of reaction now? Could potentially do elimination, but we're really looking at substitution, and in particular, which type of mechanism? SN2. It's a big, bulky leaving group. It has to be forced out. Okay, so we'll typically run under SN2 conditions once we've formed that. How did we form that? That's all your addition and elimination stuff that we've been looking at. Okay. Be aware you will likely see the abbreviations for these species. Okay. So your mesyl chloride, MSCl, your triflate chloride, TFCl, and then the tosyl chloride, which for those of you that have seen it in other class, also known as HOTS. Okay. HOTS. It's an alcohol instead of a chloride, and an instructor, a friend of mine, likes to refer to it as HOTS. Yeah, he's weird. It's okay. Questions? Okay. So this was kind of a typo here. Those of you that took 152 here, that might look familiar on the right. I was helping somebody in the tutoring center and apparently typed it into my slides. Do we need to see the acid-catalyzed transesterification reaction? Because I personally really don't want to do it. Okay, it is in your textbook. All it is a bunch of proton transfers, okay, which are started here. If you guys need to see it, I have no problem going through and doing it. It's the question. Do you guys need to see yet another mechanism of protons coming on and off a structure? Thank you. I very much appreciate that. This is an odd one. I can definitely see why a name would get associated with this. This is known as a Bayer-Villiger oxidation. You start with a ketone, and you add what kind of species? Dang it, it's already up there. Oh, hey, look at that person. What kind of species? You didn't look very fast. That species is known as a peroxy acid. Peroxy because of the oxygen-oxygen bond. The acid is because we have carboxylic acid. Where have we seen peroxy acids before? Forming what? Yeah, last semester. Epoxides. And we sometimes see them associated with radicals. That tends to be much less frequently, though. When we're looking at our peroxy acids, we're really tying them to our epoxides. Okay. Under these conditions, we've got kind of a bizarre reaction happening here. If we take a look at that product, what happened? Do we have an epoxide? No. Not only do we not have an epoxide, but somehow or another, an oxygen decided to insert itself into that carbon-carbon bond. Okay. That's a bit bizarre. And I completely agree with you. I think it is nutso bizarre. Okay. When we look at these reactions, short of memorization, there isn't a whole lot else. Okay. So we will look at the mechanism here in just a second, but I really think it's just going to be easier to deal with these by memorizing. The reference right underneath is part of your memorization thing. If we now make that a CH3, that compound is an asymmetric ketone. Okay. Asymmetric meaning because on one side we have a phenyl ring, the other side it's CH3, so it's not symmetric through the carbonyl. in asymmetric ketones, the oxygen will insert itself according to something known as the migratory aptitude. This is ultimately why I think you should just memorize it. The migratory aptitude is incredibly nonsensical. Okay? So if you already have to memorize a migratory aptitude, just memorize the reaction. Okay? So our oxygen inserts according to the migratory aptitude. So if we take a look at this new structure that I've got drawn, where should the oxygen insert itself? Onto the phenyl side or onto the methyl side? You might say methyl, that would have made sense to me too, but if we take a look at our migratory aptitude according to the Bayer-Villiger oxidation, the methyl group is the least likely to migrate, which would mean the oxygen should insert itself to the phenyl side. And the result, ooh, you're not going to like me for this. I may redraw the whole thing. Oh, sorry, and thank you, Ed. You would end up with that ester product. Okay? So all you're really doing is inserting the oxygen according to migratory aptitude. You have to have the migratory aptitude nailed down to figure that out. You might have tried something about stability of the species in the migration, but then I don't see why tertiary is more stable than hydrogen, or why tertiary is more stable than aryls. What does aryls stand for? Aromatic structures, rings. Okay? Not cycloalkanes, but with the double bond, with your aromaticity, those alternating double bonds. Okay? In a symmetric ketone, doesn't matter.
Wasn't that what the thing you first had up there was? Or you erased it there?
Doesn't matter where the oxygen inserts itself.
No, because it's the same.
It's the same on both sides. It doesn't matter which side it inserts to. It's only when it's asymmetric do you have to worry about it. That's why I erased it and drew the CH3 in there. I didn't have time to draw it in, so I had to do it by hand real quickly. Okay? Questions on that? So my question is going to be, this is all about the nucleophilic addition and elimination chapter. How is this reaction a nucleophilic addition and elimination? What do you think the or let's try the electrophile. What do you think the electrophile is in this case? Carbonyl carbon. What is our nucleophile? The oxygen of our peroxy acid. That oxygen comes through, attacks the electrophile. We end up with our tetrahedral intermediate. Okay. That tetrahedral intermediate, we look all the way down to this guy, because most of those are just protonations and deprotonations, is right here. Okay. The migratory aptitude is now referencing those two carbon-carbon bonds. Which one migrates to our oxygen? Okay. And by so doing, would then have to kick out the rest of the peroxy acid. Completely obvious and sensical mechanism. That's a joke. Okay. Bizarre reaction, kind of neat for the results that come out of it. Your oxygen acts as your nucleophile, attacks, you then get this migration happening, and that's your big clutch interesting step. Everything else is just a transfer of hydrogens. Okay? Questions about it?
Why does it migrate?
So a good question would be, why even bother? Why should it even consider migrating? Okay, well, once it's attacked, what is the highest energy structure or highest energy bond in all of this is that oxygen-oxygen bond. Okay. Even when we get to the migration period, we still have that oxygen-oxygen bond. Okay, that is our high energy bond. Why migrate? Well, through every other step before the migration, what do you have? A high energy oxygen-oxygen bond. What happens after the migration? You don't have that oxygen-oxygen bond. Not only do you not have that oxygen-oxygen bond, what do you have in that structure? A resonance stabilized negatively charged oxygen. Okay. So that's your big irreversible step because you go to form very stable species. So the whole migration is happening to remove the reactivity of that oxygen-oxygen bond. It's kind of the idea of a methyl shift. Okay? Our methyl shifts are our hydride shifts. Okay? It is a rearrangement. Other questions?
So is it saying that the hydrogen in the migratory outsuit, the hydrogen is more likely to move and then...
Our hydrogen is more likely to migrate than any other group. Okay? In this case, the groups that we are choosing to migrate are both aromatics.
Right.
To get hydrogen to migrate, what functional group would we have to start with? We'd have to start with an aldehyde. That's the only case where you have a hydrogen to migrate. That structure would be an aldehyde. It's the only time you'll see it. Okay? Questions? Okay. This should look familiar, right? We've talked about these. Aldol condensations. What happened? Walk me through it. Because I don't want to walk anymore. Come on. The base removes a hydrogen. Why can it remove a hydrogen? It's an acidic position due to that alpha position. Okay. We then have a resonance stabilized nucleophile, which can react with a second molecule. To give us our charged intermediate. That can pick up a hydrogen, and we would end up with the aldehyde and an alcohol, also known as the alcohide. Did you shake your head because it was that bad of a joke? We have the aldol product. The aldol very often goes through and does the condensation to get us to our final product. And we've done the aldol condensation. Okay. What happens if I make that hydrogen a CH3 here? Well, we went through and made that hydrogen a CH3 all the way through. We do the exact same. I can just erase it. I don't have to draw a CH3. There we go. What happens if I add OET?
Would do something along the lines of migratory stuff.
What was that? Say that again.
The OET is like a leaving group.
The OET is a leaving group. How different is that chemistry from the aldol? What do you guys think? Like, whoa, that was amazingly different. That's like Bayer-Villiger. Or like, yeah, that was boring. Why'd you show me that? Those are your two choices. And yes, you must say it with that emphasis. Come on, I got you to do Hell-Volhard-Zelinsky. How different is that chemistry? Pretty much the same thing. I agree. I think it's entirely the same thing, and I think there's no reason that we should be giving it its own name. It is referred to as a Claisen condensation. It is identical chemistry. Okay? I think I drew the product officially wrong at the end. Okay. But you're going through and doing identical chemistry. There is nothing drastically different about starting with an ester than using an aldehyde or a ketone. The only thing that really changes is once you've done that nucleophilic attack, you now have a leaving group in that other piece. Okay? That is it. Which means your end result doesn't get you to an alpha-beta unsaturated carbonyl anymore because you don't end up doing that elimination. You eliminate the good leaving group as opposed to the crappy leaving group of the hydroxide, okay, to form the alkene. So you just end up doing your full exchange across. Okay?
So the aldol is more of a reduction, whereas the Claisen is more?
No. Don't look at it like that. They aren't, yeah. It's not a reduction or an oxidation. Okay. Why is it not a reduction or an oxidation? We haven't increased or decreased electronegative atoms to our individual carbons. Okay. We get pretty much a one-for-one swap. We lose the hydrogen and we trade it for carbon. Difference in electronegativity is negligible. There isn't a reduction or oxidation reaction. Right? When we dealt with the aldols, what were some things that popped up with those? Let's see, do I talk about that right now? Oh, we look at the mechanism, which we just looked at. Okay. What were some things that popped up with the... Okay, fine, I'm just going to skip to it. Aldols. If we take a look at that top reaction, that is an aldol standard reaction. What was the issue with that reaction? You guys did this in class. That very first reaction, what's the problem with it? What's your product? You get 4 products. There's 1. 1, 2, 3, 4. I think I drew that one right. There's 2. So we get lots of possible products coming out of this. Okay, and that kind of sucks. Okay, how did we fix that? Okay, we broke it into 2 steps. And not only did we break it into 2 steps, what did we change? We watched our base choice to make sure that we selectively formed an enolate. Once we selectively formed the enolate, then we could react it with our electrophile to end up with 1 product. What's going to happen when we move down to the Claisen? We're going to run into those same issues. So we want to be more careful or as equally concerned about the order in which we run our reactions for our Claisen as we were with our aldol. Same problems pop up. Okay? So you have to be very careful about your choice of base and the order in which you run the reaction, okay? Because we want to make sure that we only end up with 1 product. Along the lines of choice of base, don't look at that slide. Okay, now you can look at it. Okay. When we look at that bottom situation, What happens if I add OET to that ester compound? Okay. And actually, I want to simplify that a little bit. Okay, so we can deprotonate a hydrogen here, which can then give us our nucleophile. We can then do our nucleophilic attack. Right? Nucleophilic attack. We have our intermediate, right? Then what happens? Electrons come back down, kick out the leaving group, and we'd end up with a possible product, right? Oops, 1, 2. Everybody see that? What did the OET act as? Base. Does OET always have to act as a base? What else could it act as? A nucleophile. Where's your electrophile? We can break the pi bond, reform the pi bond, kick out our leaving group. What's our product? Is that different than our starting material? It's OET versus OME. It's an ethyl versus a methyl. When we run our Claisen reactions, we have to watch out because we can still do nucleophilic addition and elimination reactions at the carbonyl carbon. So the choice of base, when you go through and run these reactions, you will notice has a very common pattern. 1 oxygen, how many carbons in this? 2. Take a look at the choice of base. 1 oxygen and 2 carbons. Because if that decided to act as a nucleophile, we want to make sure that we aren't changing our starting material unnecessarily. Minimize the amount of chemistry possible. Okay. There's another thing in this reaction that I didn't call attention to in our mechanism. Okay, or I haven't called attention to yet in our mechanism. Let's go through, draw the nucleophile here real quickly. We'd have our negatively charged species here. This can go through and react theoretically with another species. We would end up with that sounded very ominous. Fine, don't laugh at that. See if I care. Just go home and cry. Right? Big ugly mess. Kick that back down, kick out that leaving group. I'm listening. Whoops.
Oxygen.
I had too many species there. Couldn't the oxygen?
Would it do that?
We'll talk about that in a little bit too. We would not be able to form a ring with this one because it's unstable. You don't have a good ring. You need a 5 or 6 membered ring. We look at that overall result. Is there anything to drive that reaction forwards? We started with OET, we end with OET. That's an equilibrium reaction. An equilibrium reaction that has no driving force to go forward. What's your yield going to be? Pretty bad. The yield for most Claisen reactions is actually pretty solid. Okay? This one, its stability is so bad that it actually does not go forwards. What is different about this starting material? So this will be the question we end on. What is so drastically different about this starting material versus the starting material that we started the whole system of Claisen reactions out with? So I'm asking ethyl ethanoate versus this material. That is what we will end lecture on. We will start with that on whatever that next day is, Monday. What is the difference that allows that top reaction a pretty solid yield, and if we tried to do the same thing with that other reactant, it would give us a pretty crappy yield?